In this section, we're going to look at some methods of numerical integration, and these are methods by which we approximate a definite integral when we can't find a formula for the antiderivative using our methods of integration. So examples of such functions are e to the x squared and cosine x squared, which don't succumb to any of the methods we've studied so far. Now, we've actually already studied 3 of these methods of numerical integration in Calculus 1. When we wanted to approximate a definite integral, we could use a left endpoint approximation, a right endpoint approximation, or a midpoint approximation to the definite integral, which is the net signed area between a and b, where a and b are the limits of integration. So here we're looking at the function y equals 1 over x between a equals 1 and b equals 4. So we're looking at this function over an interval of length 3, and we would like to approximate the area beneath the curve. One of the methods we learned in Calculus 1 was left endpoint approximation, where we approximate the area under the curve with a certain number of rectangles, and we decide how many rectangles to use. And if we use 6 approximating rectangles, then we must carve the interval up into 6 equal parts, and these form the bases of the rectangles. And for the left endpoint approximation, the height of the rectangles is determined by the height of the function at the left endpoint of each of these subintervals. For the right endpoint approximation, the height of the approximating rectangles is determined by the height of the function at the right endpoint of these subintervals. And of course, for the midpoint approximation, the height of the approximating rectangles is determined by the height of the function at the midpoint of each of these 6 subintervals. And notice that with all of these approximations, you get an approximation to the area under the curve by adding the areas of the approximating rectangles. And the important word here is that this is an approximation. And you can see at the bottom of this diagram what the approximated area is and what the exact area is, which is something we can calculate in this case, or at least get a very, very accurate approximation. So you see there's a small amount of error here for each of these approximations. And we see with the midpoint approximation, the sum of the approximating rectangles is 1.37693, whereas the exact area is approximately 1.39. So we're off by just a little bit, in fact 9.36 by 10 to the minus 3. Now, of course, if we increase the number of rectangles here, we get a better approximation. And as I increase the number of rectangles, you can see that the approximate area is moving closer and closer to the exact area. And when I get to 100 approximating rectangles, there's very little difference between the approximation and the actual area. And this is also true for left endpoint approximations and right endpoint approximations. Now, we're going to introduce 2 new methods of numerical integration or numerical approximation in this section. One is called the Trapezoidal Rule and the other is called Simpson's Rule. And instead of using approximating rectangles, we're going to use approximating trapezoids for the Trapezoidal Rule, and for Simpson's Rule we're going to use something more general where the curve is fitted to the top of our approximating construction using a parabola. Well, let's review the formula we had for the midpoint rule in Calculus 1. If we're trying to get the midpoint approximation to the definite integral from a to b of f of x dx, then we first split our interval from A to B into n equal parts, where n is the number of approximating rectangles, and the base of each has length delta x, which is b minus a over n. And the endpoints of these subintervals, when we divide, are given by xi. x naught is the left endpoint, it's a. x1 is a plus 1 times delta x, x2 is a plus 2 times delta x, etc., etc. And of course the midpoint of these subintervals is going to be the sum of the endpoints divided by 2. So the midpoint of the first subinterval is x0 plus x1 over 2, and this we're going to denote by x1 bar. So our midpoint approximation to the definite integral from a to b of f of x dx with n approximating rectangles is going to be the sum of delta x times f of xi bar. So that's the sum of the length of the base of each approximating rectangle, which is delta x, times its height, which is f evaluated at the midpoint. And this gives us a nice tidy formula for our midpoint approximation with n approximating rectangles, namely delta x times f of x1 bar plus f of x2 bar, etc., etc., plus f of xn bar. Let's use our formula to find an approximation to the integral from 1 to 4 of 1 over x dx with 6 approximating rectangles. Now, we've already looked at the picture of this in Mathematica, but let's apply our algebraic formula to find the actual approximation. Delta x here is b minus a over n, so it's 4 minus 1 over 6, which is 1/2. So that means for each of these approximating rectangles, the length of the base is 1/2. And the next step is to calculate the xi's. x0 is a itself, it's 1. x1 is a plus 1/2, that's the other end of the first subinterval, which is 3 over 2, and I keep adding 1/2 to get the next xi until I get to 4. Now I must calculate the midpoints of these subintervals. So the first subinterval runs from 1 to 3 over 2, and its midpoint occurs at 1 plus 3 over 2 over 2. So this is equal to 5 over 4, and the midpoint of 3 over 2 and 2 is 7 over 4, etc., etc. Now, to get the heights of the approximating rectangles, I evaluate f at each of these midpoints. And f is just 1 over x, so 1 over 5 over 4 is 4 over 5, 1 over 7 over 4 is 4 over 7, etc., etc. So now I have the length of the base of each approximating rectangle is 1/2, and I have a list of their heights here. So I multiply the base times the height and add, and that gives me my approximation. So plugging this into our formula, we have delta x times f of x1 bar plus f of x2 bar plus f of x3 bar plus f of x4 bar plus f of x5 bar plus f of x6 bar. And when we plug in the numbers and add, we get 1.376934177, which is what we saw in Mathematica.